The last of our sorts, the quick sort, is at the same time very simple and conceptually maybe perhaps more complex than any of the other ones we've talked about. So from a simple standpoint, we have this idea of a pivot point. A pivot being is some value that you grab in your list. It's going to essentially be a random value because you're just going to grab the center of the list, and you're going to sort the list based off of that pivot point. Everything that is less than that is going to go on the left-hand side. Everything that's right of that's greater than that, is going to go on the right-hand side. And so, if when I partition based off that pivot, that means when I sort the list from then on, everything's going to be more or less where it's going to end up in the final mix. There's some randomness inside of here. If your pivot is not very centered, then you might be doing unbalanced work on either side, but it works out in the wash. It works out pretty well overall, so long as we'll see the data's fairly randomized going in. So the quick sort starts like many of the other sorts. We have a left and a right here. So I called low and high before, and that's to allow me to use left and right here for quick sort. It makes a little bit more sense when we talk about this pivot sense. So notice here, the left actually starts off at -1. So 0 is the first item. The left actually starts off at -1. We'll see why here in a second. So the pivot is the middle value. It doesn't matter what the pivot is outside of it's just a value grabbed on it. It really doesn't even matter where you grab it from, but the middle is a nice place to grab it from, as good as any place else. So in this case, the pivot ends up being I, and I swap the pivot out in this form of the quicksort algorithm. There are a couple of versions of this, but this form of it, I swap the pivot to the end. It makes sense as we go. We're going to get to see why as the algorithm goes on, but really it just gets it out of our way, and then we can just work up and down, if you will, the list from here. So the rule is we start from the left and we push our left pointer up until it's greater than the pivot. So the first time we always advance it by 1. Okay, we start at -1, we always advance to the next one. And in this case, the S is it's already bigger than the pivot of I, so we stop right there. And then we push left, the right pointer left, until we get to the smaller value. So, it starts off on the pivot, so it pushes left, so U is not lower, but F is. And so once we get to F, then we swap those two positions. F and S get swapped. All right, and then we continue on so long as the left and the right are separated, as long as they're not equal. So or the right is less than the left, possibly as well. So the left moves up until it finds the next one higher than the pivot. So O is the next one. The right one moves, to the left. We keep squeezing together. They're the same. That one's less than it, so we swap those. Again, we automatically kick up the left every single time, and so we move this down. Well, again, it's big. It's here. The N is definitely smaller than the R, but it's bigger than the pivot. So we're moving this down until we get to each other. So let me back up. Let me back up here for a second. When this moved down to this point, I wasn't comparing N to R, I was comparing N to the pivot. And so then I compare N to the pivot again, T to the pivot, and R to the pivot. None of those are smaller than the pivot, so we go all the way down, and we're equal, and we end that cycle. So since we're done pushing those together, since we're done partitioning is the phrase that's being used here, we swap that location, our stop location, with the pivot. And so now we know everything to the left of the pivot is less than that location. Everything to the right of the pivot is greater than that location. So F and G are less than I, T and N, O, S, U, R are greater than I. And so it doesn't mean that everything's sorted, but everything to the left is less than everything to the right at that point of the pivot. So we know the pivot is in its right spot wherever it's going to end up. So at that point, we then sort the stuff to the left, and it doesn't really matter. The F and the G end up in the same spot. They actually get moved around in the meantime, as we'll see in a second. But then we go sort the right. So let's walk through this process one more time just to make sure you have it in your head. So again, the left and right come in. The left comes in -1. So, we're sorting here 0, 1, 2, 3 to the end. We started at 2 because we're always going to increment that once before we start it. The pivot is the middle spot, O, and so we move the pivot all the way to the end. And so we're going to push the left one larger until it is bigger than the O. So we're moving it up. T is bigger than O. We've found our spot there. Now we're going to push this one till it's smaller than O. So it moves past U, S, R all the way up to the N before we get to be smaller than the O. And so at that point, we swap those two out, and that's it. So our left side automatically moves up, but it keeps moving up until it's larger than the O. And so we skip past that N, but we now have the two of them together. So we are done with that. We switch our pivot back down. And so now we know everything to the left of the pivot is less than it, and everything to the right is greater than it. So again, we recurse and we sort these two, not the whole list, because we already know that those are sorted in some way before us. And then we sort the back of the list. And that's just the same process we follow over and over again. Now, the quicksort is really quick. It does a really, really nice job because of the partitioning and moving things around. And each jump, you can see, it moves everything into its relatively correct position. There is a risk with quicksort. If you have a list that comes in already sorted, it tends to be a bit of a problem. So if we look at this, we have our low and our high, and our pivot ends up being in the middle, and we swap that out. So now we've immediately broke the ordering of the list. We don't know that when we're sorting something. We don't know that it's broken, but it is what it is. You move it over. But then immediately we go to the middle and we swap it out. And then we do the same thing for the left, and then we do the same thing for the right. So we end up basically pushing things out, pushing things back without ever doing anything, and a whole lot of intermediary steps in the meantime. So on a small list like this, it's no big deal. We waste a little bit of time. We go through, move stuff unnecessarily. But where it becomes an issue is if you have a very, very, very large list, because there's a whole lot of recursion that's happening here. And so if you use the quicksort on its own, and you follow the tests that I've given you, the tests are a randomized list, a sorted list, and an inverse sorted list to give you, especially on the timing list, I should say, to see how the timings work out. And so for that in order list, if you're using a really big list like the 10 or 20 or 50,000 that it comes with by default, then you have a chance of getting a Stack Overflow exception. Either in Java or C or whatever language you're using, it's all the same. And what happens is you're making so many recursive calls that you use up all your memory space for stack. It doesn't happen every time either. It's not guaranteed to happen. It's not like if you set it for 10,000, it's going to happen every single time. It might happen sometimes, it might not. You can drop that number down to 5,000 or whatever, and it'll fix it, but it'll ruin your ability to get accurate timings. You need to do some big lists to get accurate timings. So the way traditionally folks handle that in the quicksort is you just shuffle the values ahead of time. If I don't know if it's sorted or not, then I just simply go through and I randomly change. In my case, I give you some code that randomly changes half the values. So randomly selects 50% of the values and moves them to some other random location, and it sorts it enough so that way you won't blow your stack. But just remember that as you're doing your work. If you get some Stack Overflow exceptions, it's not necessarily you're coding wrong or you're even doing the recursion wrong. It's just simply saying that if the list is ordered, it could be a problem. So in general, the quicksort is very, very quick, but only if it isn't sorted already. And so to be safe, you have to shuffle it first, which then adds a certain amount of overhead to the list. So if you absolutely know there's very little chance of your data being sorted already, this is a great sort. It's really, really quick. And the final phase of this, you'll get to play with that notion a little bit. You get to play with the timing. You'll get to play with it a little bit more. But I just want you to give you that heads up, that warning. If you are passing the quicksort for the basic exercise, but then it fails on timing, don't fret, especially if it's a Stack Overflow exception. That's not a problem. I've actually added a shuffle method that you can sort in there just to add it through there, and then you can play with where you want that to use it or not later on. All right, so that's a introduction to the quicksort. I hope that you have fun building that quicksort. It's the last one, at least as far as this recording in 2020, last one I'm having you do. And that will wrap up your ability to sort. The next step after you have that done is we're going to talk about how do we analyze these algorithms? How do we know which one's mathematically better than the other ones in average situations and help us be able to determine which ones are the best for any given use?